Okay,
Our
hello.
next speaker is Marcin Szamotulski, also known as Mikut on Twitter. Marcin has a lovely blog at kut.me where you can find articles ranging from the evaluation of folder prime in the container package to articles explaining how different algebras are used in Haskell. Besides programming, Marcin also enjoys playing some jazz on his guitar. And today, Marcin will talk to us about pipelining in the type protocol package. Marcin?
Okay, thank you, Benoit, for introduction. So this talk will be about networking, but in a quite peculiar way because we're using quite a lot of type level machinery for writing network code, which might be surprising. So I work at IOHK, where we write a decentralized application that runs across the globe, and the nodes needs to communicate with each other. We need something that is efficient and type safe at the same time. So this blog post is actually a literate Haskell file, which is checked by JC. It has very few dependencies, more dependencies as like the language extensions that are used, which is quite a lot. This talk is organized around a very simple protocol that is a ping-pong, which has 3 states. At the start, the client has an agency, which means the client can send a message, and it sends the message ping. Then the agency is changed to the server, and then the server is able to send a message, which is pong. So there is a ping pong set request reply style, and the agency is the thing who can send the next message, and the final state is the terminating state, where nobody is allowed to send any message anymore. The protocol terminated. We're done. So when we're back in the idle state, the client can choose whatever it wants to do. It can either terminate the protocol by sending message done, or send next ping. And normally, in normal circumstances, without any pipelining, how the protocol would evolve, there would be several ping and several pong responses going one after the other. And the problem with this approach is that there's quite a lot of latency that is taken away from the application. Like, we need to block and wait for each response, and pipelining solves this kind of problem, and it allows to. It's about sending all the messages that we want to send at the front, and then waiting for replies. So there's kind of a shuffle between order of messages, but not every shuffle is allowed. Only some of them are possible. So in this example here, we send 3 pings at almost at once. Then we wait for all the responses. They probably come in a very short time, and this pipeline protocol will execute probably 3 times faster than the non-pipelined version. So yes, the first thing why it's useful is for latency hiding, which I already mentioned. Another point why protocol pipelining is useful is how the network is actually used, because networks work very well when we put a constant pressure on them. Like, like TCP buffers will not shrink. The TCP window will not shrink, and this kind of problems can be avoided by using pipelining. But there are some challenges because when we pipeline messages, and each message is a transition between some states, we no longer have a continuous flow of transitions that compose as arrows or functions. We break this in some way, and if we want to have a type level safety around the transitions that we're trying to encode, that will be a challenge, and the talk is actually about this challenge. And what pipelining must do, it must keep the relative order of requests and responses, but can mix both groups. So this describes what the shuffling, pipelining can introduce. So first we'll try to encode a non-pipeline protocol. How can we encode that in Haskell? So the ping-pong can be represented by a single lifted data type. So lifted meaning that this stidle, stbusy, and stdone are actually types of kind ping-pong. These are not values, but types. And then we have three messages, which are terms or values. We can send a message simple ping, message simple pong, or message simple done. And each message encodes that it's a transition between some states. So ping was transitioning from the idle state to the busy state, pong from busy to idle, and done from idle to done. And then if you want to describe a ping-pong client, which is an application that starts as a client, so it is only allowed to send ping messages and receive pong messages. So this can be encoded simply as this recursive data type that takes the message, the send message takes the simple ping-pong message as an argument of this given type. So message simple ping-pong from type st idle to some state st that the transition defines, and a continuation, which is the recursive type. Or it can receive a message, and this client can only receive a message which takes from the busy state to idle state, and we expect a message. So this is a lambda, which returns a continuation. So it's a simple ping-pong client, or it can terminate the protocol. So these are the three constructors that can be used to write an application, a ping-pong client application. So the non-pipeline version would look like this, very simple. It sends a message, which is send simple ping. Then it expects to receive a message pong. So this is the lambda that received the simple message simple pong, and does it 3 times, and then it terminates. That's a very simple way to encode a protocol that can send and receive some messages. But if you want to encode pipelining, what we actually currently do in framework that we're using live in our system is the following encoding. We split the sender and the receiver into 2 parts, and we only have to track how many messages we already pipelined. So for that, we have this recursive or inductive natural numbers that are used on the type level only. And the simple pipeline ping-pong client can either pipeline as a single message, so it needs to be presented with the message. Then it needs to get the receiver of that message that will be executed separately, and the continuation. But we need to update the counter that counts how many messages we already pipelined, because we're just pipelining a message. And then we have a constructor here that collects responses. If we pipeline something at some point, we might want to receive the result of that response that we hope to receive. And here, the receiver, the ping-pong receiver, which is at the bottom of this slide, has this type parameter C, which describes what is the output of the receiver. So we know that in this case, we expect just a message pong. And we want to produce from that message some value. For more complicated protocols, this might be some more interesting computation than here. Some case analysis on messages received, or multiple messages received during the receiving process. If you want to have this use this API for writing a simple pipeline client, this can also be encoded, and we use this pipeline send message constructor. We present it with a ping message, and then we want to present the receiver. So this very simple implementation takes a fixed collect value. So this function, the receiver function, is just a constant function here, and the continuation in which we pipeline another message, another ping message, and the receiver also is a constant function. And then we collect responses. So we collect the first response, we collect the second response. At this state, this collect subtracts the number of messages that were pipelined. So this continuation takes n, but it constructs s of n. And this is in opposite to what pipeline does, which adds to the counter. So when we collect twice, we after pipelining 2 messages, we're back to 0 messages pipelined, and this means that we can send message done, which requires that we only can terminate the protocol when we collected all the responses. That's why this pipeline done constructor requires here that there's no pipelining at this point where we want to use that constructor. Okay, and what's the biggest problem with this kind of implementation? So it's actually the branching that is introduced by this pipeline send message. We not only need to present the next message that is sent, we also need to present the continuation that will receive all the transitions that we expect. In this case, from busy state to idle state. And when we want to execute this somehow, we will need to introduce concurrency, and that's how our current implementation is dealing with that. It's a kind of nifty solution, actually. but it has its own limitations, especially that that it requires this type C to be defined for all your protocol, or and if a protocol has multiple opportunities to pipeline different messages in different states, then this type might become big, like a big sum that has to be scrutinized. And another drawback is that you need to use concurrency where it really isn't needed, because pipelining is not about how things are scheduled on your hardware, but just the ordering of messages, of sends and replies. So here I would like to present another approach of doing pipelining. First, we need an agency. So agency is a promoted data type. We only have client agency, server agency, and nobody agency, which are types of kite agency. So this is the way of encoding who's responsible for sending a message, so that we don't want to have a situation where two sides of the protocol are expecting to receive a message, or we also exclude a situation where both protocols sends a message at the same time. And the first one would be a problem for all the protocols, because that would be a deadlock. And the second one is actually useful in some situations. And maybe I'll have some time to discuss this at the end. And then the protocol type class just describes what messages can be sent. So what are the transitions? This transition can carry data. They are sent over a network to communicate something to the other side. And they also carry the state, which is only type level property of messages. But we also need to describe what is the agency of each state. And then ping-pong protocol, we have the ping-pong type already. We defined it. It has 3 states. And here we can define all its messages. It's a ping-pong and done message, and define their agency. That in the idle state is the client that has agency. In the busy state is the server that has agency, and in the done state, protocol is terminated, so nobody has agency. It actually turns out that the agency itself is not easy to pull a nice API around it for building the framework, so to expose nice interface for users. It's much more useful. It's the relative agency, which also has 3 constructors. Is either we have agency, or they have agency, or nobody has agency. And these things are like, for the client, the we have agency will be client has agency, and they have agency will be server has agency. But for the server, it will be swapped with the other way around. And we can always compute the relative agency, knowing what is the peer role. Is it the client or is it a server? And compute the relative agency from that. So that's this relative type family. And actually, all the type safety that comes from this framework comes from properties of this very simple function. And the main property here is that you cannot have output for where both sides has agency at the same time. We'll see that in a moment. another piece of information that is needed while building a framework like that. So right now we have lots of information encoded at the type level. But in Haskell, we also need somehow to access this information. And because Haskell is not yet a dependent type language, that's we cannot just access that information very easily. But there is one particular technique that is very, very useful for that. It's there are singleton types, and this a singleton is a data type that means it has values of certain type. It's not promoted. Is a normal Haskell value, and it uniquely maps to some type. So whenever you pattern match on it, you know, you give the information to the compiler what is the type at the type level, and this reflexive relative agency is a mix between being a singleton type and something and some equality on types. So it allows us to pattern match whenever we know that the both R and R prime are equal, and do that for a certain agency. And this will be a proof for us that, for example, the ref client agency is a proof for us that it's the client that has an agency, and the relative agency is equal to the one that we want. So one of these relative agencies will be some type level computation, and the other will be the one that we expect it to be, the one we want it to be. And this ref relative agency will be a proof for that type equality at the term level. And we also have a special version of this for the case where nobody has agency. P role, there are only two roles, so you can swap between them. There is a client role and a server role, and some properties that we'll describe later on will use that duality, and we will, at the end, we want to prove some kind of duality between a client and the server, using without actually needing to say which is which. And this is what this flip agency type family allows us. So not all agencies are allowed, like not pairs of agencies are allowed. And for example, if we draw all the agencies that are possible, or the pairs which form this diagram, so we can either have that the client has agency, or a situation where we have client and server has agency, or that client has agency and nobody has agency, like all this kind of pairs. We want to have a proof that we cannot have that the client and server has agency, or client has agency and on the other side nobody has agency. We have a proof for that in Haskell that works for all protocols, which makes actually the IPI that that I presented in the protocol class very simple. I don't want to go into details of this. It's available. It's quite readable. It just requires maybe a second of thought. But for example, the exclusion lemma between client and server is given in this form, that whenever we're given relative agency for particular agency and particular relative agency, whenever we have both these types for this computation, for this relative PR of A, and relative, where we flip the agency, then we can prove that it's actually only possible case is that nobody has agency, because that's the only case where server, where this thing could agree on. And it's just pattern matching on these types, and the rest is done by Haskell. Like Haskell can prove that this function cannot have any other arguments. That is total. Okay, I'll skip over the other lemmas. Then the most interesting topic of this presentation is how we want to represent the pipelining. So pipelining can be understood in this way, that we have some kind of queue that we push our messages that we want to pipeline on one end, and then at the other end we want to collect all the transitions that resulted from sending that message. So there's clearly some kind of queue of transitions that we need to track, and that's what is about this machinery here on this slide. So the trans type. So everything here on this slide is promoted. So we only have types and kinds. So trans is a kind that takes a protocol as a parameter, and its type tr takes two states of that protocol to construct something of trans ps kind. So this just represent a transition on the type level. It says there is a transition from this state to some other state. And the Q type is type level list. It actually could be just the promoted list, Haskell list, equally well. So it has two types, the cons type, which takes the transition and the continuation of the queue, the rest of the queue, and the type of empty queue. This left triangle is just a type synonym for cons, but we also have the other operation of a queue that we can push to the other end, which is the other triangle, which this time is a type family, and it's really the same as SNOC for lists, just done at the type level. So we just pattern match on both constructors and recurse over the cons. And once we're at the empty, we put the single element there at the very end of that list. And the main API, how to construct a client that is something like the simple ping-pong or the simple pipeline ping-pong, but generalized over any protocol, goes this way. This type is called peer. It's a normal type, which means we'll construct Haskell terms. At the type level, it specified what the protocol is, what the peer role is, whether a constructor is using some pipelining or not. That's actually useful. The queue of pipeline transitions that we will expect. M, which stands for some monad that it will run in. It might be IO, it might be some different monad. And A is the result of all the protocol evaluation. So effect is just encoding the monad effect inside the peer. Nothing nothing fancy. The done constructor needs a proof that in this state st nobody has agency. This is where we want to terminate the protocol. So we want to prove that in our current state, which is this state agency of st, where we compute our agency at the given state, the relative agency for that state is that nobody has agency. That's the meaning of this type. And because it's a value, it will be a proof of that constraint. And then we present a, which is the terminating value for the evaluation. And that construct peer for this given protocol. And the only constraint here is that the queue must be empty. We can only end the protocol if the pipelining queue is empty. We cannot protocol if there's something awaiting for us in the queue. Then we have non-pipelined API to send and receive a message. So when we want to send a message, we need to present a proof that we have agency in the current state. So this is what this reflecting relative agency provides. That in this current agency, which is state agency of the state that we're in, the relative agency of that state is equal to we have agency. And then we present a message that we want to send, which carries the transition from type st to st prime. The continuation, which because it's a non-pipelined send, it also requires that the queue is empty. The continuation continues at the new state, and that's what yield constructs. And await is dual. It requires a proof that it's not we that have agency, it's that they have agency, the other side have agency, and we have to provide a continuation that expects any message from state st to st prime, and a continuation, and that returns a continuation. Okay, and then we have pipelined versions of sending and collecting responses. So the pipelined version of sending a message takes exactly the same proof that we need to present, that we have agency to send a message, takes a message as well, but the only difference actually from yield constructor is that we push a transition onto the queue that we expect to have after sending that message. So in the ping-pong protocol, when we send a message ping, which was a transition from st idle to st busy state, this transition here that we push onto the queue is transition from busy to idle, because that's what we expect after sending a ping-pong message. And this continuation here, after pushing this st prime to st double prime onto the queue, continues at st double prime. So this allows us to pipeline next message at the st double prime state. We were able to skip this st prime to st double prime transitions, not do them right now, but to do them later. And we need a machinery to be able to receive these transitions that we push onto the queue, to collect them, and we will be collecting them from the other side of the queue. So that's what the collect constructor is for, because it's about receiving messages. The proof here is that we need to present about the agency is the same as in the await constructor. We have to present a proof that it's the other side that has agency. I'll skip over the first constructor or the second parameter of this constructor. Maybe we can talk about it in a session after the talk. And then the next thing is that it allows to receive a message, and this message we have to think what kind of transition it is. So we want to construct something that has type that the queue at the very front has a transition from st prime to st double prime. So we know that we can expect a transition from this type st prime, that there's something there that can come, but we cannot actually expect what is the end of that transition of that message. The other send might send us transitions that go to different states, not just a single one, like in the ping-pong message. So that's why this message that we expect is from type st prime to some other next state. When we receive that message, we can subtract this st prime to st next transition from the front of the queue, which means now we change this front to this transition from st next to st double prime. So it used to be st prime to st double prime. Now at the front we have st next to st double prime, because that's what we received from the other side. Since we only subtract here, but we never actually removed anything from the queue, we also need a constructor that allows us to remove identity transitions. So that's what the collect done is for. Whenever we have at the front of the queue, we have tr st to st, which is an identity transition, we can subtract it using this constructor, and these two constructors allows us to receive messages that were pipelined at some point. So let's see how we could use that to write a ping-pong client. So here we first yelled messages, like we yelled, which means send. We send 3 ping-pong messages, ping messages, and then we want to collect them. And for collecting, there's a function that allows to do that. It takes a continuation that continues from the idle state. It takes a queue as argument, which might be long. We don't know. But what is important that it continues at the idle state, and it constructs something of this type. At the front of the queue, it has this transition busy to idle, and what it does, it just collects a single message pong, and then removes that transition from the front of the queue. And once we collect 3 messages, the queue is empty. After we send 3 messages, we collected all of them, so we can terminate the protocol by sending message done. Now we're in the st done state, so we can present a proof that now nobody has agency, and the protocol terminates, returns a unit value. That protocol was very simple and wasn't able to show to show more aspects of pipelining. We'll need a bit more sophisticated protocol. So here's another version of the ping-pong protocol that allows also to send message busy that do not change agency. So once a server has agency, it can send message busy over and over again until it sends a message pong. So this protocol has exactly has the same types for its state, like they're wrapped in a new type wrapper to be able, so that we can have another instance of the protocol class. And the messages are either these are messages of the ping-pong protocol, which is the message ping-pong constructor, or this additional message busy. And states are the agency map is actually the same as the other protocol. Can we write a pipeline client for this protocol? And actually, it turns out that we can. We pipeline here 3 ping messages. So this part looks the same. Then we want to collect messages, and this version of the client tries to compute how many busy messages the server sends us, and return it as the protocol computation. So this int computed by this protocol is how many busy messages the server sends us along all execution of the protocol. So the first collect, it takes its first argument is the current number of messages received, of the busy messages received so far. So because we haven't yet collected anything, it starts at 0, and it takes a continuation. We takes the number of the messages received in current evolution of the protocol, and returns the continuation of the protocol. And here, when we want to construct the collect, the continuation function that received the message from the server, it has 2 cases. Either the message was a busy message, which means we need to continue collecting, because we want to collect all the messages before continuing. Or it might be a pong message, at which point we know that we're in the idle state, so we can terminate the collection and just return the number. Just call the continuation on that number of how many messages we constructed so far. So that's why this continuation function of collect receives the number of currently collected message busy. Okay, that's actually quite nice that we can encode this kind of logic inside recursive data type. The previous API that we used, and I presented shortly at the beginning, would be more isn't that nice for doing this kind of logic. And the framework also provides some proofs of correctness. One of them is the non-pipeline duality. It's at the lower half of the slide. So whenever we have 2 peers that both are non-pipelined, both their queues are empty, they both start at the same initial state. One returns something of type A, the other returns something of type B, and the only difference is that one is a client, the other is a server, or one is a server, the other is the client. So this is where we're flipping the agency, and we can construct a total function that just returns a monadic computation that will return A and B. So these are the values produced by both protocols, and a proof that both sides terminated the protocol. And the proof actually isn't that difficult. it might be challenging to present it in a session like this, but I'll encourage you to read through it. It's not that difficult. It's just a recursive function that goes over its arguments, and it's using the agency proofs that we have to exclude cases that we can exclude, like when both peers have agency or things like that. Another very nice property of this framework is that whenever we're giving a peer, which is an application that might use pipelining, we can actually remove it, which means construct another peer that this time is non-pipelined. So we know that it's not using yield pipelined or collect at all in its term. The proof here is more tricky, but it's also straightforward when it's written. Like all these kind of proofs are challenging where they're not done, but when they're written, they become much simpler. So it's much easier to read and analyze than to actually write when there's nothing yet done. And the very general theorem, because previously we have only non-pipeline duality between non-pipeline clients, but because we can remove pipelining, we can prove the same property about the duality theorem about possibly pipeline clients peers, just by removing the pipelining from each side. Okay, so what are the final remarks here? It turns out that this duality theorem really heavily relies on the fact that the encoding of messages is one-to-one. If there is a non-injective encoding, that can lead to deadlocks. So the deadlock freedom that is guaranteed by the duality no longer holds. Are non-injective encoding useful? Actually, it turns out they are. In our software that we're writing, we have to deal with simultaneous TCP open connections. It's a condition where both sides of the TCP connection try to open the connection at roughly the same time. And because we have a range of distribution of servers around the globe, it happens more or less frequently. And we need to have a way of dealing with that. Through non-injective encodings, we found a way how to use this machinery. Though some guarantees are no longer true, though this initial protocol that runs is very simple, so it's easy to analyze and be sure that everything will go fine. And another interesting discovery here is that when I started to work on that, I wrote mostly things in Haskell. Then I tried to encode the same things in Agda, and that simplified implementation quite a lot. I discovered a simpler way of encode things that turn out to be still possible in Haskell. And because Agda has a much stronger type system, which allows to express ideas clearer in its term. That was the key feature here. And acknowledgements goes to engineers from Well-Typed. So Alex Veith, who was the person that introduced us with this way, with this recursive way of encoding protocols, and Duncan Cutts, who contributed quite a lot to some of the ideas we've been working there. So the two links are for the presentation, and there's also a branch that I'm slowly working on that eventually will run on our servers. Yeah, that's it.
Thank you, Marcin. We do have a question from, I believe it is Simon. And the question is, when a protocol speaks of agency between a client and a server, could those parties be generalized for peer-to-peer protocols? There is a second part, which is it correct that the client and the server aren't hard-coded in the framework?
No, they're not hard-coded. Like when one will write an application, one will decide whatever side wants to write using the same type. Although we actually, in this rewrite, we provide type aliases, which removes all the proofs from the constructors. For example, if you look at the yield pipeline, whenever we fix this PR, which stands for P role, which is either client or server, this proof is fixed for every protocol. So it can be provided once we know what the role is. So we use, forgot the extension, sorry. But we provide terms that allows to construct this without providing the proof. Like the framework can do that for you, which makes writing clients and servers a bit easier. But at the very bottom, it uses the same API.
Okay, thank you very much. I don't see other questions, but if there are questions, there is a spatial chat room